Jordan's Lemma assignment 4. This assignment is absolutely very expected one. Let's start. Here the example is, prove that integration from minus infinity to plus infinity cos of x dx over x square plus a square into x square plus b square is equal to pi over a square minus b square into e the power minus b over b minus e the power minus a over a, where a is strictly greater than b, strictly greater than 0. Mind blowing. Alright, we will integrate fz is equal to, now tell me what is my fz. Here it is very easy, cos function without any power. So in the numerator I will write minus infinity to infinity e the power iota z. Yes, because m is equal to 1 here. Okay, let me write only the function here first. Over, yes, this is z square plus a square into z square plus b square. We will integrate. Okay, you can apply integration sign or not, it's up to you. So z square plus a square into z square plus b square. Well, this is a long contour C, right? Of course, from negative r to positive r along the real axis and then followed by the semicircle tau. Now finding the poles, clearly fz has poles at, yes, just take the denominator equal to 0, you will get poles at z equal to. Alright, this is plus minus a iota, and for the second bracket, this is set equal to plus minus b iota, of which only z equal to a iota and z equal to b iota lies inside the contour C. Now I'm going to calculate the residue for both these poles, for a iota and b iota. So residue of fz at a iota. Of course, I'm not having any power in the denominator, so I can use that short trick method for calculating the residue, and that method is, this is your function f of z, right? Just put the value for z in the numerator first. So this is e the power iota z, that is iota into a iota, that is a iota square, which is negative a. And then you just have to derivative the denominator with respect to z, just derivate it and then put the value of z over here in the denominator, right? After derivating. So when you derivate this, you will get, of course, this is first function, right, into the the derivative for the second one. This is 2z, then plus second function into the derivative of the first, which is again 2z, at z equal to a iota. So this is equal to e the power negative a. Now first bracket will be 0 because z equal to a iota, that will cancel out. For the second one, this is a iota, this b square minus a square, right? And this is 2a iota, okay. 2a iota and b square minus a square. Similarly, the residue of fz at b iota will be e the power negative b over, just by symmetry I'm writing here, you can check and calculate, this is a square minus b square. Now taking the sum of the residues, so this is equal to e the power negative a over 2a iota, this is b square minus a square, plus e the power negative b over 2b iota into a square minus b square. Cool. So this is equal to 1 over 2 iota. I'm taking common a square minus b square. This will be e the power minus b over b minus e the power minus a over a. Well, now apply the Cauchy residue theorem over here. Next step. By Cauchy residue theorem, we get integration over cfz dz. This is equal to 2 pi iota times the sum of the residues, and we have calculated the sum of the residues as 1 over 2 iota. This is a square minus b square into e the power minus b over b minus e the power minus a over a. Now this contour C will be first along the real axis. This will become e the power iota x our function. So this is x square plus a square into x square plus b square dx plus, now along the tau I have to use z variable. So this is e the power iota z over z square plus a square into z square plus b square dz. So this is finally equal to this 2 will be cancelled, 2 iota that will cancelled out, and the remaining this is pi over a square minus b square into e the power minus a over, this is e the power minus b over b minus e the power minus a over a. Very fine. Now since this 1 over z square plus a square into z square plus b square is tending to 0 uniformly as z tends to infinity, and it is also a meromorphic function in the upper half plane, right? So this integration, the second one, along the tau, when I put the limit r tends to infinity, this will be 0. That's what the Jordan's lemma says. So this integration is 0. So I have to let r tends to infinity in equation 1. So letting r tends to infinity, this my negative r will change to minus infinity to positive, and this is e the power iota x over x square plus a square into x square plus b square dx. This is equal to pi over a square minus b square e the power negative b over b minus e the power negative a over a. Fine. Now because I need cos in my integration, the required integral, I need cosine function, so I have to equate the real parts. Now I know that this e the power iota x is what? This is cos of x plus iota sine of x. If you write e the power iota x as cos of x plus iota sine of x, and then you have to just and then you equate the real parts, you will get minus infinity to infinity cos of x, because there is no imaginary part in the right hand side, so that will be 0. So equating the real parts, I will be getting cos of x over x square plus a square into x square plus b square. Oh yes, this is what my given integral is. So this is equal to pi over a square minus b square e the power minus b over b minus e the power minus a over a. Yes, that's very fine. There is no need to change or from 2 to y 0 to infinity, because already in the given integral I am only having minus infinity to infinity as my limits for the integration. So I am ending up here only. Thank you so much for watching this video. Have a nice and blessed day. Thank you so much. God bless. Do like and subscribe for the latest videos. Thank you. Thank you.